In this video we look at the FP3 work on hyperbolic functions. The specification states that we need to know the definition of the basic hyperbolic functions, we need to know their inverse functions, we need to do some basic calculus, so that's differentiation and integration with the hyperbolic functions. We then also need to be able to use the properties of the hyperbolic functions to derive identities. You'll find that the work on hyperbolic functions carries through over lots of different questions in the course of FP3, so several of the topics that are mentioned here will actually come up in other videos as well. So here are our key facts. We've got the definition of sine and cosh x and the various different definitions of tanh x. You ought to be familiar with the graphs of these functions. We've then got the remaining three hyperbolic functions: coshec x, which is 1 over sine x, sec x, which is 1 over cosh x, and coth x, which is 1 over tanh x. The identity cosh squared x minus sine squared x is always equal to 1 is given in the formula booklet and is very important. There are two results that are immediate consequences of that. The first one is obtained by taking the initial identity, cosh squared x minus sine squared x is equivalent to 1, and dividing through by cosh squared x. And the second identity is obtained by taking the first one again and then dividing through by sine squared x. We have the hyperbolic function equivalent of the compound angle formulae, and we have the three formulae that are given again in the formula booklet for sine 2a, cosh 2a and tanh 2a. We need to know the derivative and integral of the basic hyperbolic functions, and we also need to be familiar with the inverse hyperbolic functions and their forms as logarithms. We also need to be aware of the fact that the equation cosh x equals p has in fact two roots, and they are x equals plus or minus cosh to the minus 1 of p if p is greater than or equal to 1. So let's move on now and have a look at some examples. This example comes from the 2009 paper, and we have to solve the equation cosh 2 theta equals 6 sine theta minus 3. Now the formula booklet gives us two really useful pieces of information. The first one is that cosh 2a is the same thing as cosh squared a plus sine squared a. So cosh 2 theta is cosh squared theta plus sine squared theta, and that must equal 6 sine theta minus 3. The formula booklet tells us, but we should also know, that cosh squared x minus sine squared x is always equal to 1. So cosh squared x is the same thing as 1 plus sine squared x. So cosh squared theta here can be replaced by 1 plus sine squared theta. So simplifying, we have 2 sine squared theta minus 6 sine theta plus 4 must equal 0. Divide through by 2. We've got sine squared theta minus 3 sine theta plus 2 equals 0. So that's sine theta take away 1 times sine theta take away 2 equals 0. So we've got sine theta must be 1 or 2, which means that theta must be sine to the minus 1 of 1 or sine to the minus 1 of 2. But we know that there are the logarithmic forms for sine to the minus 1 of x. So sine to the minus 1 of x is ln of x plus root of x squared plus 1. So we can say that theta is either going to be the ln of 1 plus root 2 or ln of 2 plus root 5. The marking for this question, well, there are 3 marks for obtaining the quadratic equation in sine theta, 2 marks then for obtaining the 2 possible values for sine theta, and the final 2 marks for having those values for theta expressed in the required form. So let's move on and have a look at a second example, and this comes from the 2012 example. We're being asked to prove that the integral between 0 and 1 of x sine x dx must be equal to 1 over e. From your knowledge of integration in C4, if the integration had been x sine x, you'd probably be thinking in terms of using integration by parts to do the integration, and we are certainly going to use integration by parts for this example as well. So, the integral between 0 and 1 of x sine x, we'll start off by integrating the sine x and get cos x, leave the x alone. So we've got x cos x between 0 and 1, and then we need to take away 1 times cos x. So the 1 is the derivative of the bit that we left alone, and the cos x is the integral that we've already done. So we've got x cos x between 0 and 1, take away the integral between 0 and 1 of cos x. Cos x integrates just to give me sine x. Put the limits in. So when x is 1, we've got, for the first integral, we've got cos of 1, take away 0 times cos of 0, which is 0. For the second integral, we've got sine of 1, take away sine of 0. Sine of 0 is 0, so that's just cos of 1, take away sine of 1, or e to the 1 plus e to the minus 1 over 2, take away e to the 1 minus e to the minus 1 over 2, which leaves me with just e to the minus 1, which is 1 over e. The mark scheme for this question has 2 marks at the beginning for making use of integration by parts, and then 2 more marks for getting down to the correct integral. So getting down to x cos x minus sine x is the integral, and then the final 2 marks for convincingly coming through to the value 1 over e for the value of the integral. So let's move on to our final example, which comes from the 2010 paper, where we are considering the function sine 2x minus 14 sine x plus 8x for values of x which is greater than or equal to 0. So the first thing we're asked to do is consider f dash x, the derivative of f. So differentiating through, we can say that f dash x is going to be 2 cos 2x minus 14 cos x plus 8. Now again, the formula booklet reminds us that cos 2a is cos squared a plus sine squared a, so the 2 cos 2x here can be replaced by 2 lots of cos squared x plus sine squared x, and we've still got the minus 14 cos x plus 8. And then again, the formula booklet reminds us that we've got cos squared x minus sine squared x is always equal to 1. So in this case, we can replace the sine squared x here by cos squared x minus 1. So we've got f dash x is 2 lots of cos squared x plus cos squared x, take away 1, take away 14 cos x plus 8, which simplifies through to 4 cos squared x minus 14 cos x plus 6, and take the factor of 2 out. We've got exactly the expression we were looking for. For a stationary point, we need the derivative to be 0, So that means we need 2 cosh squared x minus 7 cosh x plus 3 to equal 0. That factorises as 2 cosh x minus 1 times cosh x minus 3 equals 0. So we've got cosh x equals a half or cosh x equals 3. But we know that cosh x is always greater than or equal to 1. So cosh x equals a half has no solutions. Cosh x equals 3 has got 2 solutions, namely x equals plus or minus cosh to the minus 1 of 3. So x is plus or minus 1.76. But the function f is only defined for positive values. So the function f has only got one stationary point, and that is x equals 1.76. Now we know f dash x is 2 cosh 2x minus 14 cosh x plus 8. So the second derivative is going to be 4 sine 2x minus 14 sine x. When we put in x equals cosh to the minus 1 of 3, which is roughly 1.76, we obtain the second derivative of f as 28.28, which is certainly positive, which tells us that the stationary point must be a minimum. Marking for this, well, there was one mark at the beginning for simply differentiating f, and then one mark for carrying through to the required expression for f dash x there. There were then 3 marks for realizing that when we solved f dash x equals 0, we ended up with either cosh x equals a half or cosh x equals 3. And then we needed to convincingly come to the fact that there was only one stationary point, and that that stationary point was x equals 1.76 to gain the last 2 marks for part B. And then for part C, we needed to differentiate and obtain the second derivative, insert the value of x for the stationary point, and show that that came out to be a positive value, and deduce that it was a minimum, and that gave us the 3 marks there.